Hello. All right. How's it going? Getting close to the end. All right. So just a quick, I'll do a quick intro. Was anybody not at the keynote this morning? One or two? Okay. Okay. So all right. Maybe. I'll do a quick intro of the topic, but let me just walk you through what I'll talk about, and we'll do this very interactive. Just feel free to jump in, ask questions at any time. We got Lee that's going to help us with the mics, so we can record the questions and everything else. But feel free to ask any questions. The topic that I wanted to talk about is active-active geo-distributed applications. Redis has done replication for a long time. The master-slave replication that we have in the product we use for HA, and we also use it for geo-distribution. But there's a new type of replication that is the underpinnings of the technology for active-active distribution, so that you can read and write anywhere, and all of these peers can actually receive these reads and writes, but reconcile all of those differences. And when we looked at this problem a while back, the answer was CRDTs. So we looked at a lot of the techniques. I'll actually talk about what techniques exists out there to do stuff like this, like active-active. I want to compare and contrast a little bit and just tell you a little more about why we ended up in CRDTs, et cetera. Has everybody been to Carlos's talk at one? Good. Okay. So maybe we'll tie back to some of the things that he's done. He's obviously been in this area for a long time. I'll talk about more the application of it to Redis, so you can see it working in action, et cetera. Let me introduce myself really quick. I've been in Redis for a while. I am a database guy, database geek for a long time. Worked on many of these products. This is my 6th database product. I always like to ask how my previous products are doing. So how many people have worked or remember Illustra? Nobody. Okay, that's not surprising. How many people worked with Informix? Perfect. I was there. How many people worked with SQL Server? I worked on SQL Server for about 10 years. Perfect. It's not my fault. That product sucks. All my older buddies are going to kill me now. How many people worked with or used Couchbase? Okay, so it's Couchbase is memcached. So you guys can see the pattern. I like RAM, I like DRAM, I like in-memory, a lot of this kind of processing. And obviously Redis is the best database I've worked on. So, I'm not just saying that, but it's really the best database that I've worked on so far. There's one other thing that I want to introduce quickly. We talk about generally Redis, and everything that I'll show you will look like Redis and will smell like Redis, except what I'm actually about to show you is going to exist only in Redis Enterprise. It's the product that we actually ship as part of Redis Labs. Redis is the open source version of our product. Redis Enterprise is 100% compatible with Redis. It looks like Redis, but we enhance and expand its capabilities to be able to give you some of these capabilities. So the capabilities I'll show you are available today. You just need to use Redis Enterprise, not just Redis, to be able to get there. So I'll give you a quick tour of Redis Enterprise, and then want to talk a little bit about the architecture, because especially the replication architecture is something that you want to see visually before we actually start talking about these globally distributed databases and how all of these pieces kind of fit together. And then the rest of it, I'm going to try to do it as much as on the command line as possible, so you can see the differences and we can experience different data types and how they work and what happens. And very similar to the morning, I'm actually going to simulate 2 clusters, and we'll kind of inject some faults, cut off their application, do some updates, and let them kind of reconcile and see what happens. But that's the idea with most of these things, is that I just want to kind of pop the hood a little bit and show you what happens with different commands. All right, so I work for Redis Labs. This event is the great work of some of the folks who actually work there, but this is generally a Redis open source event, so we've got lots of people. But we do the most amount of contributions to Redis. Obviously, Salvatore and the rest of us who work on the engine are the ones that are building the open source. We built this Redis Enterprise capability to give you a couple of additional capabilities on top of Redis. So we enhance a couple of things about it. One is high availability. We actually have a different way of assembling and orchestrating the cluster. As opposed to Redis cluster, we give you a set of capabilities that are a lot more aggressive in deciding, looking, and orchestrating kind of the health of the cluster. So the failover times you will see are much better. We also give you these added capabilities like active-active replication that doesn't exist in the open source. Obviously, security is one area where we spend quite a bit of time. So there's, as opposed to Redis, there's separation of admin versus application security that's in there. We also have an architecture that manages the connectivity architecture of an application to Redis. So we'll actually shard databases to many different shards across many different nodes, but your communication and your application could actually work with it as if it is a single instance of Redis. You get with this one endpoint, all you need to do is just talk to that. It feels like even though there are hundreds of Redises that are actually satisfying the calls that you're making, we're just hiding a lot of that detail, and these are the parts of the product that we change to give you better scalability, especially with larger applications and hundreds of middle-tier servers connecting into the same database and working with it, et cetera. So that's where the perf and scale enhancements come from. Finally, we provide a lot of the modules that you see. Some of them are by us. There's quite a few outside of Redis Labs as well. But things like search, graph, and some of the things that you've seen at the keynotes, these are the things that we spent quite a bit of time on to enhance and provide as an extension to Redis. So here's the architecture. Every node looks the same in Redis Enterprise. And the red layer of this cake that you see is Redises. Those Redises look very similar to Redis open source, but we actually do make changes to it. One of the things that Yiftach talked about this morning, which is how we use DRAM and the 3D crosspoint technology or the NVMe SSDs. We changed the kind of memory and storage architecture of the product to be able to adapt it to these kind of new pieces of hardware so that it's much cheaper to store much larger data sets. You don't have to buy DRAM for everything that you do. And we do changes to the durability mechanisms, et cetera, within the product. So from an application standpoint, it still looks like Redis, except there's quite a few administrative controls that you have as to what kind of durability and what kind of consistency and guarantees you actually want from the product can actually be configured through that. The blue layer of this architecture that you see is where most of the orchestration and additions that we have live. There's a proxy that will manage the connectivity, as I just talked about. There's an orchestrator here that will look at the health of each node and make sure that we can detect an unhealthy node and create quick consensus to be able to keep or fail over the shards that live there, et cetera. So all of the orchestration or adding a new node or removing an existing node, these are all the things, orchestrations that we have to do. And those are the things that happen at the blue tier. There's quite a few watchdogs to keep the environment running. Even if a process or a node or a rack fails, it can actually rescue you out of that situation. Now, I would go into a lot of detail on different parts and components of the architecture, but I just want to kind of unpack what the replication architecture looks like. There's local replication that we have. So among the nodes of a cluster, what we call a cluster lives in a given region. And we make a lot of assumptions. We actually make assumptions that nodes will actually have very low latency when they're talking to each other. So typically, under a millisecond latency. But we set up a replication capability among them that will do master and slave replication. So your writes go to the master shard, and slave will actually receive everything that you write to the master. That is there for high availability. So if anything happens to your master copy of your data, we promote the slave copy to a master your system continues to work. That's the protection. That's the failure domain it's actually trying to protect you against. So node or rack failures, we can actually protect against that. But it's possible that the roof of your data center could collapse, and that's when the WAN replication comes in. So if you wanted to deploy Redis across multiple regions, either because of high availability or you want your data to be closer to the users that you have, like the ones in Europe shouldn't actually cross the Atlantic with a 180 millisecond latency just to write to a West Coast data center, you can actually use the WAN replication to cross that boundary. WAN replication makes other assumptions. It says, oh, there's going to be hundreds of milliseconds of latency between the source and the destination, and there's going to be a lot of disconnects. So the replication mechanism that we've built for crossing that kind of boundary makes a lot of assumptions about the fact that there's going to be failures and resumes and restarts that we have to do. And we better be careful about not having to require like starting from the beginning of time and replicating everything from scratch when something like that happens. So these two replication strategies can be combined. So there's always a local cluster. That local cluster is highly available, but if the roof collapses, that replication is useless. So we actually go, we give you this added replication, the WAN replication, to protect you against all of these things. There's also two types of WAN replication, just to make it complicated. So there's one where you can actually have a CDN-like experience. So you can write to this one copy, and there could be a lot of slaves that you put out in the world. The nice thing is it's a cascading replication topology. So A can replicate to B, and then B can, in turn back and replicate to C, and C can replicate to E and D, and so on, right? You can actually set this up. This is great if you want all of your content everywhere, but you don't have a lot of writes other than to the main site. So it's great for scaling out reads. But if you want scale out of reads and writes, CRDT, Redis CRDTs is the mechanism. And this is the bidirectional replication that we were talking about this morning. So Replicove is kind of this unidirectional. You will see just a single point arrows, but the unidirectional replication that we have in CRDTs allow you to have many different participants all replicating to each other. All right. So this is an example of a Replicove setup. This is like the CDN version, where the European version, North America version has the writes, and then it shoots all of these as aggressively as the local replication over to remote sites. But we're bound by the laws of physics, so it will take a little longer because the ping latency is a little higher to Europe. It will take a little longer for that update to get there. The interesting thing about both of these technologies that I'll show you, or both of these that we'll look at, is the cluster sizes can be completely different. So you could have 7 nodes in the US and 55 nodes in Europe if you want, right? We don't care. You can size your cluster to the capacity that you wanna manage. So it's perfectly possible to have different capacity. And this is true for CRDTs as well. Every participant doesn't have to have a symmetric, identical setup. We're just going to let you kind of manage that depending on the load and read and write traffic that you have in each geography. This is an example of Redis CRDTs. So a lot of people use Redis CRDTs for just pure failover cases. So I've got East Coast and West Coast. I've got a shopping cart. And even in that case, I may assume that I'm the only one writing to that shopping cart. I'm the one shopping. But when a failure happens, I don't want that shopping experience interrupted. So I will have another copy someplace else. And in case West Coast fails, I can continue shopping on the East Coast. And I can continue writing to that shopping cart and reading from that shopping cart, no problem. So this is that setup. Or you can have really, truly geo-distributed applications that are doing distributed writes. There are lots of conflicts. These are things like counting retweets. There are many people who like the same content as I do in the US. I'll retweet something that's going to add 1 to the number of retweets, and they're going to retweet, and they're going to add some numbers to the number of retweets. So in those cases, we're actually building a distributed count or a distributed set or a list, et cetera. And those are the cases where a conflicting write is the nature of the application, right? It's not like the shopping cart where it's just me shopping. It's like I am the only one writing, or my session state is the only one that's being kept. It's actually a session state that's global, counting all of these different events that are happening on the same key itself. So before I explain Redis CRDTs, it's always good to put the full picture of what type of geo-distribution techniques exist in the world. And that's what I'm going to do in the next couple of slides. So geo-distributed, we're not the first database that is going to geo-distribute your databases, et cetera. This has existed for quite some time, and there's been different techniques used to do this. If you're a relational guy, you probably have heard of a protocol called two-phase commit. How many people know what two-phase commit is? Okay, so it's, if you want pure consistency, it's essentially a transaction that takes all the parties and communicates with them and tells them, everybody prepare to commit. And then they all say yes, and then the second phase is, okay, let's commit. And that's what the protocol does. It's just kind of played out over and over again, depending on your transaction. Now, the problem with two-phase commit is there's so many message exchanges that have to happen that you can't do more than a handful of things a minute, right? Relational databases typically will actually use this technique to do writes. It's great because it's consistent. If one of the participants is not there or can't write, they're all going to fail. There's some undeterministic states in two-phase commit too, but they're rare. But the biggest problem with a technique like this, it sounds great, it sounds very easy to program against. The problem is you can't really run high throughput. And number two, if any participant is missing, your write will fail. You can't say I'm going to have a distributed transaction with 3 participants. If one guy is missing, the whole system is down. There's nothing anybody can do until that participant also shows up. There's another technique called quorum-based writes. This is what Cassandra does, Dynamo does. For distributed writes, and quorum-based is a very similar technique, except AP systems like Cassandra will basically say, look, I've got 3 copies of my data here in data center 1, another 3 copy in data center 2. So if you want to consistently write, you better write to majority of my replicas. I've got 6. You at least should write to 4 so that when voting happens or if something fails, there's a good chance that I will be able to recover it. Quorums have different levels, but let's assume this geo-distributed quorum of 4 replicas you have to write to. So quorum writes typically in a geo-distributed sense, if you want consistency, will need to write to at least 4 of those copies that exist. Now, from everything I said, I guess you will get the same conclusion, is like it's also quite expensive to write 4 times just for the sake of consistency. So this is extremely chatty as a protocol. The quorum techniques usually are. It can give you consistency. So in the nice cap triangle, you get C and P. But if any participant is not available, if data center 2 is not available, there are not 4 copies you can write to, because you have 3 copies in one data center, and everything will fail. You can't write once you can't catch a quorum. Right? So these are problems with CP-based techniques. They give you a comfortable, consistent view of the world. The problem is they're unavailable. They're by nature not available techniques to geo-distribute your writes. Now, there's also AP techniques that are fairly common. I've worked with a few of them. One of them is called last writer wins. This is, in fact, what Couchbase does. Last writer wins uses essentially a technique. Couchbase is a database that has JSON as the data structure, so it's a document database, and you can actually do a bidirectional replication with Couchbase. But when a conflicting write happens, so let's say you're retweeting something, and the tweet is the JSON document, so within there's an attribute that counts the number of retweets, and everybody's incrementing them. The last write wins technique is about taking one of those copies and finding who was the last writer, and then making that the winner. So the system reconciles to one answer, that's true. The problem is it may not necessarily reconcile the answer you want. So if there were 100 retweets in Europe and 5 retweets in the US, the answer is either going to be 100 or 5. It can't be 105. So the system is not designed to be able to do those things. And last write wins is a crude technique. Sometimes works when you don't have any other information, but it's got 2 problems. One is this crudeness of the technique, because within a given document there's a lot of attributes, and every attribute's behavior is slightly different. And number 2 is that the distributed clock is a big problem. They drift, clocks drift, even on machines that are side by side. across geographies, even if you have NTP, even if you have a lot of techniques to try to keep them similar, there's going to be drifts that are at seconds level, right? So if I have a shopping cart and I happen to be writing to the East Coast and or West Coast, and then suddenly some failure happens, I start writing to the West Coast, I could even conflict with myself because replication may not necessarily replicate all the information that I wrote to East Coast or West Coast all at once. So you could, even in a shopping cart case, it's actually, the geo failover can be unsafe with these kind of techniques. Now, last technique I'll talk about is MECC. MECC is something that CouchDB used, not to be confused with Couchbase, but CouchDB used. MECC is a technique where you basically leave it to the developer to resolve the conflict. So every write is a drift or a new version of your data. And every time you write, you fork it. Fork the copies of the data. As a developer, you have access to all of them. You have to decide which copy you want to use. So let's say you're going to retweet. You have to find the copy that you want to add one to in that tree of structures, and there could be many different writes. It's very difficult, and it's extremely verbose, and it bloats the schema. It bloats the storage quite a bit because you have to keep a lot of versions of the same document all the time. And unless you have very few writes, it's really not a good technique to use. So most of the time you find yourself, you're not able to reach even reasonable throughputs with a technique like that. So the interesting thing about all of this is that CRDTs take an approach that is somewhere in the middle. What CRDTs provide is the ability to have smart conflict resolution by understanding the developer's intent and the structure. So the early implementations that you will find were actually not generic, like a database having a CRDT enabled structure. They were mostly techniques used by application developers on specific applications. TomTom is a good example. When we were looking around, TomTom's implementation of CRDTs is purely on the client side. They understand kind of traffic information, and when they get a lot of these traffic information from different sites, they actually need to merge them together to get a good, accurate picture. Now, there are conflicting details on the same stretch of road, on how much traffic there is, or how fast you can go, et cetera. So that data structure has a very good indication of how you would like that merge from different sides and different pieces of the fragments of the information to give you a good idea as to how you want to merge that information. As a developer, you can actually kind of, based on that traffic data structure, you can actually make a lot of choices. Now, the interesting thing in Carlos's, Mark's, and the CRDT research, what we've seen is that there are emerging data structure techniques that come out. So more and more, as you kind of develop applications, there are these patterns that emerge. So CRDTs gave us a way to basically say, oh, okay, so on a list, there's actually a fairly reasonable set of things we can actually assume. If people are using a set or a list, based on the commands they have used to add, remove, or kind of change the structure, we can actually see if there is even a conflict that we have to worry about. So anybody who knows the set data type in Redis, set is a bag of unique values. So you can only have one geon and one rotem, and that's it. You can't add a second geon into that set. So if all of us in Europe and US are adding new items to that set, there's actually no conflict unless the values themselves collide. So we can do that. Or if you look at incur, for example, incur is a method in many of the different parts of Redis. You can either do it on a counter type, or you can do it on hash values, or you can do it on a score of a sorted set, for example. Right? The incur method gives you a good indication of what the developer's intention is. They're trying to increment from where they are. They are trying to add 5 or 10 or 100 to the existing value. So when we actually receive these conflicting writes, we can take a look at what the developer's intent was. If they use the incur method, we know what that intent was. If they use the set method, we know what that intent was. And based on that intent, we can actually be smart about how we merge the changes back into this structure. And that's what CRDTs provide. So they do not require us to have all of the sites that participate available. So if there's data center 1, 2, and 3 that are participating in a Redis CRDT database, data center 2 never cares whether data center 1 and 3 are available. If they're not, That's perfectly fine. We'll just keep going. So unlike the Quorum or the two-phase commit, CP-based mechanisms, this does not require availability of the participants. But there are very well-defined rules per data type as to how we're going to make the conciliation happen, so it's not as crude a tool as last right wins every time, right? So that's the core of the technique. So one of the things that I want to say about this is that, Redis obviously, there are two things that immediately it kind of lights up in my brain and hopefully in yours, is that, things that are fast is going to happen in Redis. So this technique that we have better be fast, right? I want low sub-millisecond latencies. And the other thing is throughput. Like, I need to be able to do 1 million operations a second, and this thing better keep up with that kind of throughput. So the latency and throughput has to be low. That's what Redis CRDTs provide, coupled with availability, and that's the great thing. So if you've got data center 1, 2, 3, just like this picture, there's a local app that's writing locally to each one of those copies and reading from those copies locally. So those applications, as far as they're concerned, they're talking to a Redis database. It doesn't feel, smell any different. There's a couple of data types missing, but outside of that, we're just going to use the existing Redis commands to actually just interact with our databases. It's just that, the developer who wants to write this global application has to think a little bit about which structure is the right behavior for the type of application that they want to develop. So if you use lists and you do certain types of operations concurrently on both sides of that list, you want to find out and learn how the reconciliation is going to happen. There's specific. Most of them are not surprising, but there's still a couple. So, and I'm going to take some time to actually go through all of them. So let me actually skip over most of these, and we'll do this in the demo. I'll skip over this too. Okay. So one thing I want to say is the database is one thing unique, just so it doesn't confuse you when you see these multiple databases, is that in Redis databases, when you create them on the master copy, and you actually have this one database and one endpoint that you connect to. When you create a Redis CRDT database, it's a global database. So you provide multiple cluster names as you're creating it. We orchestrate how we're going to create those databases on all of those clusters. But you actually get an administrative control plane that is global. So when you actually go add another participant to the list of participants, let's say you have 3 data centers, but you want to go to 4, all of the participants are going to receive messages that says there is a 4th participant that you need to start talking to. So that administrative plane is very much a global control. But when it comes to app level access, when you're reading and writing data with the endpoint, it will feel like you're working with a single database. Like you don't actually go and work with 2 different endpoints. So each local cluster will give you one endpoint that you can actually work with on that with that local application. So there's going to be, if there are 3 participants, there's an endpoint for all of those databases in each geographies for the local application that wants to work with it. So that's the only thing. When it comes to synchronization, we also do read from the secondary if you have a secondary copy. So master and slave replication will read from the slave so that we distribute the load a little bit, but that's how the replication happens. And there's a process called syncer that sits and will actually kind of read the details from the secondary and push it to other clusters as it comes in. So it's an aggressive replication technique. It compresses and encrypts that script, but it will try to get your updates as quickly as possible over to the other participants in the Redis CRDT structure. So these are kind of the architectural nuances of what we have. When it comes to developing applications, the nice thing is, there's no command that's unique to us. There's a couple of small differences that I will point out. But outside of that, this should smell very much like Redis open source to everybody. And the thing to do is, so if you're a Java guy, or if you're a Python guy, or a C# guy, use the SDK that's out there. It's no different. It's the same SDK. It's the same Redis kind of clients that you can actually use. The only thing to remember is that every data type has its own conflict resolution mechanism. It's all in technical documentation. You can go read all day all about these things. And generally, there's a couple of rules about how we resolve the conflict. So one of them is we have an existence bias that we've built into the product, which means that adds win over deletes. So if an add and a delete happens to come and collide as a concurrent read, so US decides they want to add a new or update a value while somebody in Europe decides they want to delete it, US is going to win in that case. If your expiry is set in two different conflicting rights, let's say US says this item is going to expire in 10 seconds and Europe says this item is going to expire in 30 seconds win. So we have this existence bias in the system that kind of makes things live longer. You can still delete if everything you observe in the system, everything that's been replicated and has not been updated can be deleted. That's not a problem. It's just that when deletes and updates conflict, there's such a bias in the system. There is, I think that's probably the most interesting one. All right, so let me just first describe what's a conflict and what's not a conflict, because it will be instrumental in kind of getting this pinned down. So as long as there are syncs in between the sites, imagine the US data center and the European data center here. If I set the key 1 to value 1, and a synchronization happens at time t2 between these two clusters, there's no conflict. If I set the key to value 2, key 1 to value 2 in Europe, and a synchronization happens, again, there's no conflict. The set was actually able to observe the value, and while, because it has been replicated, there was really no conflicting rights here, right? We were aware that the value was value 1, and we deliberately made that value 2. So it's not a conflict. If you're reading and writing, that's not a conflict, which is what happens at time t5. And you will see that the value is staying the same. OK. So what I want to do is just quickly introduce some of the data types. But why don't I actually do that on the command line? So if you have seen it this morning, there are two clusters. I'm doing this in Docker locally completely. So speed is not going to be great, but I have the blue side representing one cluster and the green side representing the other cluster. What I'm going to do is write to both of them, and then we'll cut their network so you can actually see, I will prevent them from syncing so we can slow the time down and create some conflicting writes, and then we'll let them talk again, and you will see what happens afterwards. So one of the first things, that is an interesting, OK, let me do this one more time. OK. All right. So that's great. So set A1, yes. Oh, thank you for pointing that out. I was looking at something completely different over here. All right. Well, if I do that, I'm not going to see it. So why don't I do this? How about now? You guys can see it, right? Yep. Can you guys read it? OK, perfect. Sorry about that. Thanks for pointing that out, Lee. That would have been an interesting demo, though, right? So I'm the only one seeing it. All right, so the blue side is one cluster, and the green side is the other cluster. So I'm going to do set A2, since I did one already. If I do get A, it's 2. Perfect. They're replicating. If I do set A3, I should read 3. They're replicating, they're healthy, they're happy. Both of these copies are two different endpoints. They are two Docker images. They think like they're actually clusters. They're two separate images. So you can see if you can't read this at the top, they're there. So one of the interesting things about this is that I can say, incur on, let's say, counter 1. So you'll see 2. If I do counter 1, it set the value 3. Get counter, C1, it's value 3, perfect. Now let's do something to break the network. So I'll do network partition. What happens is I'm putting an IP table between them so they won't be able to talk. Like if I take you back to UI, which we can do. This is what the UI looks like. This is the cluster view. This is, it's kind of, you can see how many nodes in each cluster. This is one of the clusters. It's the cluster called cluster1.local. In this cluster, there's this database called the CRDB, Redis CRDB database, which actually has one thing unique, which is that participating cluster list that I mentioned. So in that participating cluster list, you see the list of all the different participating clusters. But the endpoint, if you look at this, is right here is the local endpoint for reading and writing data. Now you see this turn into orange because we can no longer communicate across the two clusters. So it's telling us replication is not happening at the moment. If I go increment, let's do incr by on count 1. Let's do 100 increment. So if I get C1, it's 103, right? If I do an incr by here on counter 1, and I do, let's say, 55, values 58. So they no longer agree. They're not replicating. Locally, I can still read and write to each one of these copies, but they no longer agree on what the final value is. So let's fix this problem. And what will happen is that the syncer processes on both sides will realize, oh, well, I can talk to the other guy. So they'll actually negotiate about what was the last thing that we actually talked about. Well, it turns out C1 was 3 back then, right? But what's interesting is one side now thinks C1 is 103. The other side thinks it's 58. Now, in a system like last writer wins, you would say, okay, is it 103 or 58? Right? You would have to pick one of the two. But because I use the incr method, the system keeps track of what methods I have actually done. And the syncers are, because of this additional metadata, able to send my intent over. So what will actually happen is that it will say, oh, we used to be at 3. We used to agree that. But it looks like you added 100. I added 55. So it should be 158. Sorry, 158. Yeah, that's true. Right? Let's see if I'm right. So green side thinks it's 158, and the other side thinks it's 158, right? And this is what's great about the ability to keep your intent, is that because you were counting, all you needed to do as a Redis developer was to use the incr method, and the system resolved the conflict on your behalf the correct way. If we were doing it for pub sub, so that's another interesting case. We can, publish a channel. Let's publish, a message called A. Okay, so let's subscribe here. I use the same name. I don't know if this is going to work. So yeah, let me just do this. Let's call this C2. Subscribe to C2. Okay. So if I publish A, you can say publish. The subscriber receives it. If I have multiple subscribers, they will all receive it, etc. This is great. In fact, I could be on the blue cluster with another connection subscribing, and that's perfectly going to be able to receive the things that I publish as well. So this is where you can actually kind of have a distributed application broadcast to all of these different copies and be able to kind of receive these messages for you. There's not much of a conflicting write in this scenario, but it is possible that I could start, I need a couple more windows for this, but I can start publishing on the same channel from multiple publishers, so the green side could actually start writing, and you will see both of them kind of intermingling their messages and communicating to each other, and they can actually send them to all of the subscribers at the same time. So multiple publishers, multiple subscribers, all being able to kind of read and write. We merge that traffic together for you, instead of picking one side or the other. This is where a last write wins like technique would not even work. You couldn't imagine what it would actually do. Set is another example that we can kind of take a look at. So no, I don't want to quit out of this. So let me clear here. SAD is another one that we can use. So let's have a set called set1, and if this was a shopping cart, you could say, I'm going to get a costume. in my shopping cart. You can see in S members, all right, sorry, let me delete S1 and start over. I have a costume in my shopping cart. If I was to go here and look at that same shopping cart, I would see the costume here too. So if I did an S add here for a mask, can't type today, and we want to do that to S1. I could see both mask and costume kind of appear on my shopping cart. But if I inject a fault here, and we again kind of pause time a little bit to simulate a concurrent write, let's say I add a mask 2 and a costume 2 to the mix. Now, on one side, I think I have 2 costumes, and on the other side, I'm going to think that I have 2 masks, right? And how would the system reconcile something like this? I used a method called sadd. So in a system where you would have to pick one side or the other, for this whole structure, you would either pick 2 costumes or 2 masks. But once we actually cure this, what you will see is that because set is a structure where all the unique items can actually live happily together, and because we use the sadd method to add new items, the system knows to keep all of these things. So you're going to see 2 costumes and 2 masks at the end when the reconciliation happens. So there's the 2 costumes and 2 masks on one side, and 2 costumes and two masks on the other side. Yeah? You can, absolutely. Please wait for the mic and ask it.
So what would happen in the event of when you had the partition? I'm curious if underneath it the CRDT you're using is a G set or something else. Because I'm curious if you do like an sadd on one for a new element and an s remove, like a remove on the other side, how is it rectified after the partition is healed?
Perfect. Let's do it and find out. So we do something called an observed remove. So if I was to add element 1 on one side, I'm not going to type it up because I know there's a couple of other things I wanted to touch on before I close, but I'll tell you what the result is. Sorry, I'll ruin this. But one way in which you can think about this is observed remove is about observing or being able to remove things that you've observed. So if there's a new item that's being added and you're removing that at the same time, you can't remove it. If this item hasn't been replicated to you yet and you're removing an unupdated or an older copy of it, you can't remove it. But if you observed it and among every participant, this item has not been updated while you were deleting it, the delete will succeed. So add wins or the update wins and add wins is our technique. So on a conflict like update and remove, or add and remove, add or update will win, and delete won't. But I could easily go in here and obviously say, you know, remove on, let's do mask. So if I do mask, you can see mask is gone. You can see mask is gone. So mask 1 is actually gone. So it's perfectly possible if there's no conflict, you can delete them. It's just that we don't want you to be deleting something that is also getting replicated. So it's not that we have a bias towards the existence update as opposed to delete. That answer the question? All right. So, sorry, yeah.
I know you're kind of going into more of the coding part, but I had a question from your earlier slides.
Yep.
On where do you see some of these use cases emerging, especially what verticals do you see the applications?
Perfect question. Perfect question. So what do people do with this, right? What can you do? Well, there's a couple of interesting challenges. So one of the ways I've actually seen people do this is voting systems. So if you're voting and you're trying to count how many people vote, and you're not going to let people vote twice on something. Sets and counter types like the ones that I showed are perfect examples, because the problem with creating sets, distributed sets, and distributed counters are just, with the last right wins system is impossible. You're going to have to program a lot. Those kind of systems will work fantastic. Another example is communication systems. So if you're doing chats, I don't know if you ever commented on something that's very heated, but by the time you actually finished writing your comment, there was like 15 other comments that came in and happened. And ordering those events are not that easy. And CRDTs can be a great way in which you could actually do it. In fact, the best example of CRDTs that I feel exists out there is Google Docs, right? You and I can be on the same document editing, and the system knows in a spreadsheet to let you edit one cell and let me edit the other cell. Or if we're on the same document, you can be on a different paragraph and I can be on a different paragraph and we can write. And that's a system that understands the data type it's dealing with and is able to merge those conflicting operations, what would be conflicting operations on Microsoft Excel, is no longer one, right? That's kind of the idea. So fraud detection and event collection system. So rate limiting is another case. If you have a rate limiting system where you have to count how many times somebody calls an API and you want to kind of stop the abuse after a while, or they paid for the silver packet and not the gold, and they get 10,000 calls a second, these are the types of things where counters really, again, come in quite a bit. You want to call how many times they did that in US versus Europe, and you want to be able to have an accurate count at some point. It's easy to use the incr method and do this, but if you want to rate limit somebody, or if you want to stop them from getting more text messages, or you want to start charging them after they get to 100 SMS messages for the month, then these are cases where you will actually find that you have to do distributed counting and distributed collection of data. These are the cases where CRDTs work well. So we've seen fraud detection, which is event collection, like your credit card gets used everywhere now that we shop globally. And being able to collect all of those events and not have a conflicting right erase some of the records is an important one. You can keep all of those things in a set. There are other examples. These are pretty much the ones that I've actually kind of seen people do. As I said, TomTom is a good example. Traffic information, merging it from many different sources as they collect, as they drive, that's another great example. But frankly, there's a simpler case, which is geo-distribution. The shopping cart example that I showed you with masks, and you don't even have to have people concurrently writing. It could be my private shopping cart, and I'm just bouncing from one geography to another just because there was a network failure or there was a hiccup with that data center. And if you fall back and fail over and fail back to the same site, there's a good chance that you can rush ahead of your writes. So your shopping cart, just your own writes, can conflict with each other. And that's the geo failover case. So CRDTs really make the geo failover safe. Even if you conflict in that case, CRDTs can actually protect you against any changes that you've made. So those are some of the cases, but great question, thank you. So I know I've got only a few minutes left. So I just want to hit a couple of the data types and show you a couple more examples, and then we'll be done. We have added one type. This is inferred in Redis, the string type, and if you ask the type of a key, it will say string. But we added a counter type. So if you use the incr method, we actually identify it as a slightly different type in the system. You can set it again, and it will go back to string. But as you use the incr method, we use a type called counter. So if I don't remember what we used here, but it was incr on C1. So if I type T1, you will see that the type of it is coming back as counter as opposed to string, which normally a key value would report back, right? So this type is new. It's just that the type is new for us to keep enough information about what you're doing with that piece of detail, but the methods remain the same. So you can use set or incr or append, et cetera, on all of these things, and we'll kind of pick the right type. So the counter behavior is a sum. Update versus delete, we talked about that. The add wins. On strings, there's not much intelligence we can build into a string. So if you're doing two conflicting writes. If I think a value needs to be A and Rotem thinks it needs to be B, there's no good answer. There's no intelligent answer I can come up with. It's either A or B. So we actually use or fall back to last write wins for strings when you actually do last write, when you do string updates. But many of the other types have much more intelligence that we can put into them. We talked about expiry. So the longer expiry wins if you have a conflicting expiry update. It's an append and append conflict, and append behaves like set in strings. We talked about this example. This is a shopping cart example, sorry, where costumes and masks kind of were written to the same shopping carts. We're actually merging in the set case all the updates that you make. Hashes behave very similar to what you see the field type is going to be. So if you get fields where you use incremented, they're going to identify themselves as counters. And if you have the same hash field incremented on both sides, we're going to apply the increment behavior to it. So if you add 5 to field 1 and 5 to field 2 in 2 different locations, we're going to end up with 10. If you use a string field, then the behavior is a string field. If you add new fields, they are merged together. So if I write a hash table that has field 1 and field 2, and someone else comes with field 3 and field 4 in another geography, when we combine them, we'll have 4 fields, field 1 to 4, that actually is combined into, all into one. Lists, very similar. You can actually, the lists are ordered, so you can actually change the order because you may add to the middle, or you may add to the top or to the bottom, or you may remove from either end of that list or from the middle. But in all of those cases, we actually try to merge as much as possible and merge the type of updates you guys have actually done. So this is an L push and an L pop conflict. And the way we kind of handle it is that your push is OK and your pop is OK. We just have to kind of keep the order of the set, but keep both operations essentially in the final result set. PubSub, we just looked at it. There's one interesting example, and Carlos talked about this a little bit in the keynote, and probably a lot more in his talk. But publish and subscribe is kind of an interesting capability in Redis. You can create a channel, publish, and you can listen or subscribe to multiple channels. But it actually kind of amplifies this ordering problem. So this case is very interesting, and we'll close with this. At time T1, US data center publishes on channel 1 and A. And European and Asian data centers subscribe to these updates. At time T2, the sync only happens between US and Europe. So Asia is kind of trying to catch up a little farther behind. At time T3, US data center decides it's going to also subscribe to this channel, but European data center, because it already subscribed, receives A. So that's perfectly fine, but European data center decides I'm going to publish to the same channel, channel 1, a B. I know it's a little hard to follow, but at time T4, you have 2 messages now that have actually been on the channel as far as Asia is concerned. Asia has not received them because it has not synced with either A or B up to this point. Now, when Asia syncs, it actually could return B first, depending on how the synchronization happens with the participants and the order in which it happens among the participants. So it may return B and then A, even though in the time horizon, if you look at the, in the sequence of time, you can see easily that A was the message that was put on the channel first, right? But the causal consistency behavior can actually give you this ability to have a sequencing done on top of things that may not necessarily be naturally happening in the random synchronization that we do. So causal consistency is a flag that you can enable on the database. And per key, what you're able to get is that on this channel, you're guaranteed that you're going to receive A, then B. Even if you receive B as the participating database in Asia, you're actually not, you're going to wait until A comes in, and then you will actually receive both of those things. So it gives you this ability to see the events as they happened in a little more consistent manner as opposed to in complete random option. There are applications that care about the order. There are applications that do not care about the order. But if you care about the order, causal consistency is great. So recap, I really appreciate it. This is not an easy topic to swallow and chew on, et cetera. I appreciate all of you kind of listening to this. But just remember, Redis CRDTs give you kind of an AP and a CP system all at once. Eric Brewer has a really nice paper that he wrote about the CAP theorem and CRDTs. Just search Eric Brewer, and he talks about how CRDTs changes the CAP theorem altogether, and how it made him rethink what the CAP theorem represents. So it's not just me saying this, it's the authorities on these topics, but it gives you an available system, at the same time much better consistency guarantees combined into data structures. We understand your intent and we can keep it, and that's what CRDTs are for. Really appreciate all of you listening. Thank you very much. Thanks for coming. Enjoy the rest of the conference.